In this installment, we're going to take a deep dive into the relationships of the mass distribution and the radius and the moment of inertia, as well as what that tells us about kinetic energies and changes. So we have three identical lumps of X, being a material. So if they're identical, that means they have the same mass, the same volume, and the same density. There's a cylinder, a ring, and a sphere. And the dimensions are given below. They are placed on an inclined plane and allowed to roll down to the bottom of the incline. We've seen videos about this sort of thing. Told this is 1 meter high, and these things are going to roll down the hill like so. So the first thing that we're asked to do is to make scale drawings on the grids above. Now these grids are what we call isometric graph paper. And we could call them 3D. So our ring, which is our cylinder is first, our cylinder has a radius of 1 and a length of 1. And if we look at all the dimensions here, the largest we have is 1.25. So here is our grid. I'm going to darken the lines we want so we can get 3-dimensional axes. X, Y. And what we'll do, since the length the radius we're told is 1 and the length is 1, we'll use 4 blocks per unit, so we know the cylinder is, if it starts here, will extend to here. And the cylinder's cross-section will be translated along this axis. We'll have a diameter of 2, radius of 1, either one in those directions. And translated along this axis, that means it'll be there and there. Next, we have our vertical axis, our z-axis, which is situated here. The radius being 1 centimeter, 1, 2, 3, 4, comes off all the way there, and comes down 1, 2, 3, 4. Like so. Now the cross section in this circle would be, the circle would go from there to there, and it would go from there to there, and up like this, and around like so. Now we can see the way this angle is drawn. If we go from here, it's going to be 1, 2, 3, 4. That'll be the length of it. And here where there's a tangent like so, it'll be 1, 2, 3, 4, like so. And from here it'll be 1, 2, 3, 4. And so we have a cylinder that looks approximately like that. So that is the cylinder to scale. Next we'll draw the ring. And the ring has a radius of inner radius of 0.75, outer of 1.25, and its length is also 1. So we have something in common there. We see how we're going to do this. All right, so we again have a length of 4 blocks. And now the inner radius is 0.75. So 1, 2, 3. So that's 3 blocks. And down 3 blocks. 1, 2, 3. And out along here 3 blocks. Out along here, 3 blocks. So this is going to look like that. Like so. That's the inner circle. Now if we go to 1.25, that's 5 blocks. So there's 4, 5, 4, 5, 4, 5, 4, 5. Like so. So now, and out this way. And now we draw like so. I think that was marked incorrectly. Mark that incorrectly. 3, 4, 5 out to here. And the place where we have this tangent would be here, and it's going to go 4. So 1, 2, 3, 4. And down here we get our tangent. 1, 2, 3, 4, like so. Now on the inside, we could go 1, 2, 3, 4. Allows us to see the directionality inside, or the hollow part, and then back to the ring itself, about like that. That's too far. So now comparing these two, we have the same mass, the same volume, same density material, and we get a sense of the scale of these things. So very clearly when we look at these two, irrespective of what the formula is, if we took every molecule in this cylinder and took all those distances, and we summed all those distances and divided by the number of particles, that would give us the mean distance. You can see in this case that many of the particles are farther than any of the particles in the cylinder, and those with the closest distance inside the cylinder don't exist in the ring. So clearly this has a greater moment of inertia than the cylinder. It becomes very apparent, especially when we notice that there are none in here, and that's where the bulk of them are for the cylinder inside that that radius. Another way of thinking about it is we could take those that are missing here in the middle. We have like this dotted red line that's maybe 1 centimeter, the same as the cylinder. We take all this material here, drill it out, and we're basically putting it on the outside of that ring. So, you know, however we visualize it, these are some of the techniques we could use to visualize what's going on, but we can clearly see now that the average radius of things in that ring is much greater than that with the cylinder. And so now when we do the sphere, it has a radius of 0.91. So this is going to be a circle in 2 dimensions. So let's say we'll make it just a little bit less than 1 here on this axis. Oops, there's a little bit less than 1. A little bit less than 1, a little bit less than 4. 1, 2, 3, 4. A little bit less than 4. 1, 2, 3, 4. A little bit less. So the circle that's on the plane looks like this. And going up the plane, 3, 4, a little bit less. And 1, 2, 3, 4, a little bit less. So that means this line comes around over there. This line goes to the back. This line goes to here. This line goes to here. And down here we have that going to that. That going to that. This going to that. And this one going to that one. Now we should probably make these dotted where they're behind. That's behind. That's behind. And that's behind, giving us a solid out there like so. And so we could, to try to get a sense of this, we could be imagining that piece of it's been cut out. So there's like a sphere there. But when we compare these now, it's very easy to see that on average the sphere has the smallest mean radius. So rank the moments of inertia from largest to smallest. Okay, so that's ring, cylinder, and sphere. The order they cross the finish line. Well, the one with the greatest inertia is the ring. It resists change more. So that means it's going to go the slowest. And so this is the ring. And since the sphere resists at least, that will be first, and the cylinder in the middle. Rank the rotational kinetic energies from largest to smallest, and rank the translational kinetic energies from smallest to largest. All right, so translational kinetic energy is 1/2 mv squared. And so it stands to reason that if the sphere gets there first, they all start at the same speed, 0. The sphere gets there first, it must have had the final the highest average velocity and the highest final velocity. So it's going to have the greatest translational kinetic energy. So from the smallest to the largest. So the largest is going to be the sphere. That means the least is going to be the ring. It's going to have the smallest linear velocity, and the cylinder will be in the middle. Now what we know at the top is we have gravitational potential energy, EPG. And when we get to the bottom, we have kinetic energy translational plus kinetic energy rotational. This gravitational potential energy has been converted to both. So what that means, the sum of these two must add up to the gravitational potential energy. So for an object, for the sphere, EK translational plus EK rotational must be equal to the cylinder's EK translational plus the EK rotational, and the ring EK translational plus EK rotational. Well, if the translational kinetic energy is the greatest for the sphere, it will be the least of the rotational. It will be least of the rotational. So it goes here, because we're arranging them from largest to smallest. So it has the least rotational, and the most is the ring. And the middle will be the cylinder. And so you could see then that if we added these vertically, in this case, in these three situations, we would have a constant for all three. So there's a lot we can do by looking at the mass and the volume and the density, comparing out these shapes. Now, it's not an easy feat to do this, to get this. When I made up this example, it took me the better part of an hour to get these measurements, to find out what their dimensions would actually be, to come up with these. But that is how we can apply basic measurements and draw some conclusions about the rotational and translational kinetic energy of rolling objects.